starting with section 6.1, which is on vector fields. So, taking a look at some of the problems in this section, we don't need to do all of them, it's just an introduction to vector fields. So the first problem is number 6, which shows the following. So for the following exercise, describe each vector field by drawing some of its vectors. So we have the vector field fxy equal to minus y comma x. And this is one that we discussed a lot in the lecture. This is an important vector field for some purposes that you'll see later. So at each point x, y in the two-dimensional plane, you have a vector minus y, x. So what does that look like? Like this is the circle of radius 1. Right, and this is the vector xy coming from the origin. This is the vector xy. So let's zoom in on that. So that's the vector xy, and this is the point x comma y. So the vector minus yx, its dot product with xy is 0. And of course it's the same length. The length is just the radius from the origin. And it's perpendicular to the vector xy. So the vector minus yx, so maybe we can put this one in red, perhaps. So this is the vector xy right here. This is the point xy. So the vector minus yx being perpendicular to that points this way. So essentially they are tangents to the circle around the origin on which they lie. So this is minus yx here. The vector here at this point is going to point in that direction, this direction, this direction, and they're all length 1 on the circle of radius 1. So we've got a vector field for the vectors on the circle of radius 1 looking like that. On the circle of radius 2, it's the same sort of configuration of vectors, but they have length 2 now. So vectors of length 2, oops, pointing the wrong way. So this kind of, I guess, a whirlpool-like vector field. Okay, that's number 6, and that's an important vector field, as we'll see later through different examples when we get to section 6.3. Number 7, x minus y. So fxy number 7. All right, well, all right, like here is the vector. So here's the point xy right here, say. And here's the vector, position vector from the origin. So that's point xy. This is vector xy. So the vector x minus y, okay, at this point, x comma y, right, it's going to have, well, the same x coordinate, but the negative of the y coordinate. So it points like this. So this is the point x, or the vector x minus y, right? Because what's their sum? Xy plus x minus y is the vector 2x, or sorry, 2x comma 0. Right, the sum of those two vectors. The head to tail sum, right? If you put the vectors head to tail, then their sum is the completion of that triangle which they make. So this is the point 2x right here. So we've got a bunch of vectors that look like that. So if we have, say, this horizontal line, if we take that as a reference, all of the vectors that appear on that line they point to the 2x on the x-axis for this point. So here, this one's going to point over here. Here, this one points double that, so that's like over here. This one points straight down. This one's going to point right here. This one's right here, right? The length from here to here is half the length from here to here. The one over here is going to point like that. And then for the vectors along this line, right, they're just pointing sort of upwards onto the x-axis. And if you took any other horizontal line, they're doing the same thing. So this vector up here also points to that point down there. This vector up here also points to this point down here. So along the vertical lines, points along the vertical line have, so at this point, xy down here, which is on the same vertical line as this one and this one, the resulting vector, the vector field, is right there. Right, so it's kind of similar looking to this vector field, but really it's quite a different configuration of vectors. What do these vector fields represent? Right. Well, in a physics type situation, what they would often represent would be you have a medium, some sort of fluid medium, and at each point in that medium you have sort of an amount of the fluid that's flowing through that medium, and these vectors represent that. Or at each point in some sort of, say, electromagnetic field, you're going to have an electric force vector pointing in a certain direction for any given point in that field. So there's different sort of physical phenomenon that are modeled by these vector fields. Let's see, 7. Was there 7? Oh, 7 wasn't assigned. I'm sorry, just 6. Anyway, that's number 7. Number 12. So here we have a three-dimensional vector field. F, X, Y, Z is X plus Y plus Z, or X comma Y comma Z. Xi plus Yj plus Zk. So in number 12, what does this vector field look like? So at any given point, x, y, z, so let's look at the sphere of radius 1, say. It's not too good. So at any given point, x, y, z, right, on any sphere of whatever radius along the origin, the vector xyz with its tail at the origin is right there. It's the radius of that sphere from the origin to that point. And now the vector field is just that same vector moved to the point xyz. So this is the vector xyz whose tail is at the point xyz. Right here, right, you'd have this point. Right here, or vector, you'd have this vector. Right here, say, you would have this vector. Right, so it's a vector field whose vectors always point straight away from the origin at any given point, x, y, z, and is essentially just, the translate of the vector from the standard position from the origin to here, move to, with its head here, you take the tail and put the tail there and let its head go where it is. Right, so vectors emanating outward from the origin. Other vector fields like related to this, so a similar sort of idea would look like this. If you had f, x, y, z equal to x, y, z, but instead you multiply that by the scalar that is the length of x, y, z, say, squared. Right? This vector, the length of f of v, so let's not write, f of x, y, z this time. Let's just write f of v. The length of vector f of v is going to be equal to, well, this one has got length 1 over length of v squared, and this one has got length, just length of v, would be 1 over the length of v itself, canceling those out. So you would still have the same direction, but the vectors are getting smaller as you go outward. So a picture of that would look something like this. So the vectors are getting smaller as you go outward. And along any sphere, the vectors have the same length. And the further out you go, the smaller those vectors get. So this would be the vector field of something like, the concussive force of an explosion. If you had some sort of explosion at the origin, right, and then if you go out here, the vector is even smaller. If you had some sort of explosion at the origin, the force that would be felt the further out you go at any given point, well, the direction of the concussive force, would be straight out from the origin, of course, but the length or the magnitude or strength of that vector would be decreasing the further out you go. Right? So that's an interesting example. Three-dimensional vector field. Number 12. Let's see, what else do we have? Number 18. Right. Given a two-dimensional function, or a two-variable function, f(x,y), or a three-variable function, f(x, y, z). So a two-variable function has associated with it a special vector field in two dimensions. A three-variable function has a special vector field associated with it in three dimensions called the gradient field. And it's the same, gradient that, we've been looking at since chapter 4. So in number 18, we've got the function f(x,y) is x squared sine 5y. So the gradient vector field, right, triangle, downward triangle, gradient f, is equal to the vector field of these partial derivatives. Partial derivative with respect to x and the x-coordinate, partial derivative with respect to y and the y-coordinate. So this vector field is going to be 2x sine 5y, comma, partial derivative with respect to y, 5x squared cosine 5y. And you could ask, what does a gradient field look like? Well, it's kind of they're kind of a little bit hard to draw, but if you do remember, the gradient vector is perpendicular to the level curves. Also, let me give an actual value there. Gradient FAB is perpendicular to the level curve fxy equal to FAB. Of course, this is a constant in 2 dimensions. In 3 dimensions is perpendicular to the level surface. So that's like the main clue as to what they look like. But these vector fields that are gradient vector fields have very special properties, which, if you made it all the way through the video lecture for section 6.3, the vector line integral for any closed curve is always 0 when the vector field is a gradient field. Or when the vector field is not a gradient field, you have that analog of the fundamental theorem of calculus. Fundamental theorem of calculus for line integrals. Number 20. Three-dimensional gradient field for a 3-variable function. So here's the function. What's the gradient field? So f of x, y, z is equal to, what was that again? X cosine y over z. So the gradient vector field is equal to the vector field whose x-coordinate is partial with respect to x, whose y-coordinate function is partial with respect to y, and whose z-coordinate is partial with respect to z. So here, this is constant with respect to x, and that's just x. So this is cosine y over z. For y, what do we have here? Minus x over z sine y over z. And then for z, what do we have here? It's going to be minus yz sine, or no, minus yx over z squared. Sine y over z. Right, the x is constant. The derivative of the cosine is minus sine times the derivative of the inner function, yz to the negative 1 is minus yz to the negative 2. Right, so this gradient field looks like this. Okay, that's 20. 26, 27 is, so number 26, is the vector field f equal to this, a gradient vector field? Okay, so sine x plus y, cosine y plus x. Right? Where did it go? There's 26. So this is f. Is this gradient f x y for some f x y? Okay, well, there's a couple different ways you can tell. Okay, the most direct way of telling is, well, just try to find the function little f. So in other words, is there f x y such that partial f with respect to x is sine x plus y, and partial f with respect to y cosine y plus x. Okay, well, let's try to find it. That's the most direct way of doing it. Here's the function. Is it a vector? Is it a gradient field? Well, let's give it a try. Let's give it a try and find it. Well, the antiderivative with respect to x for the first thing, right? Well, the antiderivative with respect to x here is going to be minus cosine x plus. That's a constant y, so the antiderivative would be x times y, plus an arbitrary constant. An arbitrary constant. Well, when you're talking about an arbitrary constant with respect to with respect to take an antiderivative or a derivative with respect to x, an arbitrary constant would be just some function of y, p of y. The antiderivative with respect to y well, for this one, minus just sine y plus xy plus an arbitrary constant. And the arbitrary constant, when you're taking a partial derivative with respect to y, well, it isn't just a number. It's just going to be some function that just has x's in it, or just a number. Okay, is there a function f that matches this? Right? Can I figure out a function with respect to just one variable y that looks like this, where this is some function with respect to x? Right? What would it be? Right? Well, fxy equal to, if I let p of y just be sine y and q of x just be minus cosine x, so let p of y be equal to sine y and q of x be equal to minus cosine x. And therefore, fxy equal to sine y plus xy minus cosine x works. To make the gradient of f equal to the vector field f, right? Here, this is xy minus cosine x plus this function of y. Over here, this is sine y plus xy plus this q of x, just a function of x. So this function works as a two-variable function whose gradient is this. So yes, fxy is a gradient field. The other way to do it is to, so this is method 1. Method 2 relies on Clairaut's theorem. Okay, if PQ is equal to gradient f, then P is equal to partial of f with respect to x, and Q is equal to partial of f with respect to y. Therefore, right, the derivative of P with respect to y would be equal to fxy. And the partial derivative of q with respect to x would be fyx, which should be equal to partial f with respect to x, and then respect to y. All right, so if the partial derivative py is equal to qx, partial derivative of q with respect to x, then it must be a gradient field. So when py is equal to qx, it must be that f is equal to gradient f for some f. You don't know which f, you don't know what the f is, but you know it will be so. So with this one, with this vector field here, for f equal to this, p is equal to sine x plus y, and q is equal to cosine y plus x. So the derivative, partial derivative of p with respect to y is just, well, 0 plus 1 is 1. And the partial derivative of q with respect to x, well, this is 0 plus 1. Right? So py equals qx. So f is a gradient field. Don't know what the function is, but we know it's a gradient field. So that's a faster check, but it doesn't give you what that antiderivative is. So method number one, kind of like it kills two birds with one stone, where, method number two, well, if method number two, if these guys are not equal, it's not a gradient field. If py is not equal to qx, then no, it's not a gradient field. So you can just stop at that point. But then again, if you do get that they are equal, py does equal qx, then it's a gradient field, and, well, you have to find what that antiderivative is. So you're going to have to do method one anyway. So, method one is often the way to go when you're actually trying to find what that antiderivative is, such as when you're using the fundamental theorem of calculus for line integrals, if you want to apply that. All right, so that was 26. 27. Find a formula for the vector field f equal to m comma n, given that for all points x, y, f points towards the origin, and the length of x is 10 over x squared plus y squared. So it points towards the origin with that length. So 27. So here is the circle of radius k. And if you take any point x, y, you want f to point in that direction, right towards the origin. And the length of f should be equal to 10 over x squared plus y squared, right, which is equal to 10 over the length of xy squared. So, fine. What's the vector that points in this direction? Back towards the origin. Right? If, this is the direction of the vector x, y. So here's the origin, 0, 0, and here is the point x, y. So this is the vector x, y. So now if I want to flip it in the opposite direction, what vector is this that points this way?
Is it the negative of each?
Yeah. Negative of x, negative of y. So that's the right direction. Which is the vector that points that way but has units length, length 1? So I want the vector that points this way but has length 1. Well, that's going to be minus x minus y divided by its length, which is 1 over x squared plus y squared, square root. Like this. So this vector points back towards the origin, okay, and its length is 1. But I don't want its length to be 1, I want its length to be this. I want its length to be that. Well, how do I make a vector of a certain length with a given direction? I take the unit vector in that direction. Which is this. So minus 1 over square root x squared plus y squared times the vector. And then I multiply it by the length that I'm looking for, which is 10 over x squared plus y squared. Right, so fxy is therefore equal to 10 over x squared plus y squared to the 3/2 power times xy. Another way you could write this, instead of writing xy, let's just write v. Instead of writing xy, let's just write v. So it's minus 10 times v, and then what's this? X squared plus y squared to the 3/2 power. What's that in terms of the length of v? The length of v is square root x squared plus y squared, the square root of x squared plus y squared. So if you cube it, right, square root x squared plus y squared to the third, then you have the length of v to the third. Well, vector field looks like that. The length of that, of course, is 10 over the length of v squared. What kind of vector field looks like that? You all know it. What type of vector field has force inversely proportional to distance squared? What type of field has force that is inversely proportional to distance squared? You all know, come on. You all took physics. The ghost of Sir Isaac Newton is floating around the room and whispering to you and telling you what? Gravitational attraction, right? The gravitational attraction. So the gravitational force between two objects with masses m1 and m2 is right? The force is equal to G, which is this gravitational constant, G m1 m2 over r squared, where r is the distance between them. Right, the gravitational force, it decays with the distance squared between two objects, and that's what this is a gravitational type vector field. The force at any here it is. The force at any given point, right, points towards the origin. So you have this mass in the center, and then at any given point, you've got some gravitational attraction of a mass at this point pointing towards the origin, right, where that first object is. Like, this is the Earth and that's a satellite or something like that, right? Or this is the sun and that's the Earth, or the moon and the Earth, or something of that sort. And that's the type of vector field that you get. It always looks like this, right? A constant over the distance to the third times the vector out from the origin. And the length of such a thing is the constant over the distance squared, right? Because the length of this is v, and the length of that is v to the third, so they cancel out and give you that. And actually, it's not just like a gravitational attraction, but this this type of vector field that points outward from the origin, but decays the further out you go, like this kind of thing. When you're talking about like the concussive force of an explosion from a given point, and that concussive force, it decays the further out you go. That also decays is proportional, inversely proportional to the square of the distance from the origin. And we'll do an example of that confirms that in section 3 or section 6.6. So it's pretty ubiquitous, this type of vector field. It comes up quite a bit when analyzing those types of things. Okay. 26, 27, 32, 33, 34. 32. For the following exercises, let f be x plus xi plus yj, which is x comma y. Let g equal minus y comma x, and let h equal x minus y. Fit them with their pictures. Well, we've actually already talked about those. Can I shrink this? I can't really, can I? There's no way to zoom out. Is there a way to zoom out? Zoom. 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 All right, good. Let's copy this. My keyboard for that. No. Well, it doesn't look quite so nice as I would like, but there it is. So we're given these vector fields. F is 32, 33, 34. So F is equal to x comma y. G is equal to minus y comma x. And H is equal to x minus y. So now we've actually done all of those, but so this whirlpool one, that's this. All right, this one where the vectors point back down towards the origin. Now, by the way, they have not drawn the vectors to length. They're not the length that they're supposed to be. They're shortened in some way. When we drew this vector field, we drew them with full length here, like this. So all the vectors should end at the x-axis. But rather than doing that, they just drew the vectors kind of smaller so that you can see it a little better. And so this one is this, where all the vectors are pointing straight out from the origin. All right, so common vector fields in 2 dimensions. Nice examples of them. By the way, are any of these gradient fields? Are any of these gradient fields? Is this one a gradient field? The partial derivative of this with respect to y is 0, and the partial derivative of this with respect to x is 0. So this one is a gradient field, right? What's the gradient? What's the function? So just as a side note, this one is the gradient of fxy for fxy just equal to xy, I think. No, not that. Fx, oh, I think I know what it is. It is 1/2 x squared plus 1/2 y squared. Yeah, 1/2 x squared plus 1/2 y squared. Partial derivative with respect to x here is just x. Partial derivative with respect to y is just y. Right, so you get that. This one is not gradient f because p y is equal to -1 and qx is equal to 1. Right, so they're not the same. So that's not a gradient field. And then this one is, again, a gradient field. Those partial derivatives are 0 again. So this one is the gradient f for fxy equal to, well, similar to this, it's just 1/2 x squared minus 1/2 y squared. Right, so so 3 vector fields, common vector fields with nice sort of visual pictures you can visualize of those vector fields. 2 of them are gradient fields in a similar way, and 1 of them is not. Okay, so just a quick introduction to vector fields. Nothing really like so so in depth with those problems. Okay. So the things get more interesting as we move on to chapter 6. Or section 6.2, we start talking about line integrals. Now remember, there are 2 types of line integrals. There are the mass-related or scalar line integrals, and then there are the work-related or vector line integrals. Calculating them, you know, they're calculated, of course, in different ways. You know, and they measure different things. 6.2. Let's get to the problems here. There are other types of line integrals as well, but these are the two main ones. There's also that vector flux line integral, but we're not going to cover that. All right. So section 6.2, number 44. Use a computer algebra system to evaluate the line integral over the indicated path. I don't think we need a computer algebra system for 44. We will just calculate it. So so how do I know it's a scalar line integral as opposed to a vector line integral? Well, the argument of the integral here is what? Is x plus y ds. Which is what? Is that a vector field? Or is that just a scalar function in x and y? Right? Is that a vector field, or is that a scalar function with x and y? No, it's a scalar function with x and y. So that is the scalar line integral. So we have number 44, calculate the line integral over C, x plus y ds, where C is given by r of t equal to t, 1 minus t, and 0. They're doing it in 3 dimensions. I don't know why. But t, 1 minus t, and 0, which is the straight line. What's the range for t, domain for t? From 0, 1, 0 to 1, 0, 0. So when you're talking about the scalar line integral, the direction of travel is not relevant. All right, so if you want to start here and end here, or start here and end here, it doesn't matter. The direction is irrelevant with the scalar line integral. So here, if we start at t equal to 0, then we'll be at this point, because this will be 0, 1, 0. And then at t equal to 1, we're right here. 0 less than or equal to t, less than or equal to 1. They don't actually give you that in that problem, but they give you the starting point and the ending point. So from that, you can deduce what the domain for t is. Okay, so remember, the line integral over c of f x y z ds is equal to the ordinary integral from a to b of f of r of t times the length of r prime of t dt. What is the line integral? So given this here, what is the line integral when f is equal to 1? What does the line integral measure when f is 1? When f is just 1, the line integral measures what? We talked about this back in chapter 3, section 3.4. Right? It turns out to be just arc length, just the length of r, when f is equal to 1. Right? When the density function for the curve is just 1 at any given point, then this line integral, this scalar line integral, just measures the length of the curve. So now we have the more general situation in which you have some sort of variable density function along the curve, and you're integrating that density function, and then your output is mass. Right? If your density is 1, then the output is just the mass of the whole thing of equal density, which just happens to be length, because density for a curve is measured in units mass per unit length. So we need all the ingredients to plug into here. So let's figure out those ingredients. Well, f of x, y, z is x plus y. Right? So f of r of t is equal to what? Well, x is t. And then y is 1 minus t. And z is, oh, there's no z there. So that's just 1. So f is not 1, by the way. F is x plus y. It just happens to, turn into 1 here. And then r of t is t 1 minus t 0. So r prime of t, the derivative, is 1 minus 1, 0. So the length of r prime of t is just a constant, square root of 2. For lines, the length of r prime is always just a constant, square root of 2 in this case, which turns out to be just the length of that line. Okay, so, and then a and b are 0 and 1. So in this case, the integral is, all right, so the integral over c, x plus y ds, is equal to the integral from a to b, which is 0 to 1, f of r of t, which is 1, times the length of r prime of t, square root of 2, dt. So it's the integral of the square root of 2 from 0 to 1, which is just square root of 2. Okay, so first example of line integral. 46. Scalar line integral, that is. So we've got this scalar line integral, x squared plus y squared plus z squared ds. So calculate line integral over c, x squared plus y squared plus z squared ds over where c is given by r of t equal to sine t, comma, cosine t, comma, 8t, t going from 0 to pi over 2. So this is that helix curve, 0 less than or equal to t, less than or equal to pi over 2. So it's only a half a turn of that helix. So it's right here. All right, this is the point 1, 0, 0 at t equal to 0. Oops, I'm sorry. It's not that helix, it's a different helix. It is this helix starting here and winding a quarter of the way around. So this is the point 0, 1, 0, and this is the point 0 or 1, 0, 8. So that's C. All right, so we have all these ingredients that we need to put into the formula to calculate the scalar line integral, f of x, y, z, x squared plus y squared plus z squared. So f of r of t is equal to sine squared t for x. Y squared is cosine squared t plus z squared is 64t squared. Sine squared plus cosine squared, of course, is 1. So you have 64t squared plus 1. R prime of t Well, the derivative of r, so the derivative of the sine t is cosine t. The derivative of the cosine t is minus sine t, and the derivative of the 8t is 8. So the length of r prime of t is equal to cosine squared t plus sine squared t plus 64. This, of course, is equal to 1, so you just get square root 65. So the line integral over c of x squared plus y squared plus z squared ds is equal to the integral from a to b, the ordinary integral from a to b, of f of r of t, length r prime of t dt. So integral from a to b, which is 0 to pi over 2, f of r of t, 64 t squared plus 1. The length of r prime is square root 65 dt. Bring that square root of 65 out front. Antiderivative here, 64 over 3 t to the third plus t, from 0 to pi over 2. So this is square root 65 times, plugging in pi over 2. When we get here, we get 64 over 8. So it's 8 pi to the third over 3 plus pi over 2 minus 0. That's 0. So square root 65, 8 pi to the third over 3 plus pi over 2. Okay, so another scalar line integral. So it was 46, 48. Okay, so let's pay attention to this one here. Number 48. So let's evaluate the line integral 4x to the third ds, where c is the line segment from -2, -1 to 1, 2. So they gave you the curve as just a description. They didn't give you the r of t. So you have to pick r of t. And here r of t is going to be a line segment from point A to point B. And there's a standard way to parameterize such a line segment, and I will show you how to do that right now. Now, it doesn't matter which way you parameterize. However you parameterize this curve C, right, there's different ways in which you can pick parameterizations. No matter how you choose it, it will always give you the same answer. Right? The answer to the integral is independent of the parameterization. Right, and that fact comes from the way in which the line integral was set up that we discussed in the lecture. So we've got c from -2, -1 to 2, 1. Okay, standard way to parameterize a line segment. Okay, the vector between those 2 points is what? All right, so here's -2, -1, and here's the point 2, 1. What's the vector between them? Well, the vector between them is 4, 2. Right? So if I parameterize like this, x is equal to y, so the parametric equations of the line. Pick the tail point, so the tail is -2 for x, -1 for y, plus t times the vector, And the t is just from 0 to 1. So you pick the vector between the 2 points, right? The slope vector between those 2 points, which is in this case 4, 2. And then you take the tail end point of the vector, and you write the parametric equations like this. xy is equal to the tail point minus 2 minus 1 plus the vector times t, for t going from 0 to 1. So for t equal to 0, we're here. For t equal to 1, we're there. All right, so r of t is equal to minus 2 plus 4t, if you want to write it this way, minus 1 plus 2t, 0 less than or equal to t less than or equal to 1. R prime of t is just equal to, well, it's this vector, and the length of r prime of t is going to be 2 times the square root of 5. This is 2, the 2 times the vector 2, 1. 2, 1 has got length square root 4 plus 1 is 5. Yeah, so 2 square root 5. Okay, so parametrizing a line segment in 2 dimensions or 3 dimensions. In 3 dimensions, of course, you're also going to have the z. We don't have it here. It's just in 2 dimensions. Just pick the vector between those points, calculate that vector, and then xy is the tail plus t times the vector v. So tail plus t times vector v for t going from 0 to 1. That's not the only way to do it, but that's, a standard way to do so. All right, so what do we have here? We have the integral over c of 4x to the third ds. Right? So what it was? 4x to the third ds. So that's the integral from a to b of f of r of t times length of r prime of t dt. All right, well, what's f? F of xy is 4x to the third. So f of r of t is equal to, and what's x, minus 2 plus 4t to the third. And a and b are 0 and 1. So 0 and 1. F of r of t is 4 times 4t minus 2 to the third. Length of r prime of t is 2 square root 5 dt. Factor out of 2. Factor out of 2, and you cube it, you get 8. So it's 8 times 8, so that's 64. Integral from 0 to 1. 2t minus 1 to the third dt. Antiderivative, you have to use substitution. But what does it become? It's going to be 64 over something, 2t minus 1 to the fourth, from 0 to 1. What's it going to be divided by? So 4 times 2 over 8, I think. Is that right? 1/8 times 2t minus 1 to the fourth. The derivative of this is 4 over 8, 2t minus 1 to the third, times 2. Yeah, that's what it is. So this is equal to 8. And then at 1, you're going to get what? You're going to get 2 minus 1 is 1. And then at 0, you're going to get minus 1 to the fourth is 1. Now you get 0. That's disappointing. 2 minus 1 is 1 to the fourth power. Minus 0 minus 1 is minus 1 to the fourth power. 1 minus 1 is 0. So anyway. So that one is 0. Why did it turn out to be a 0? Why did it turn out to be 0? Why did it turn out to be 0? So So if you take the point, let's draw that line segment, -2, -1. So -2, -1 is here. And then 2, 1 is here. I see what it is. So the line segment looks like this. Right, that's C. And as you can see, C is symmetric around the origin. Right? So the x coordinates along here are the negatives of the x coordinates along here. Right? Or the x coordinates along here are the negatives of the x coordinates along here. So we're adding up the value of 4x to the third in this direction here, and they're all positives. And then over here, it's going to be the same value, except the negatives, right? Because it's all nice and symmetric there. So if it was 4x to the third plus y, or they had some y along with it, it would be a little more interesting, this problem. You wouldn't get 0. Or if you did the integral, say, from the origin to 2, 1, you know, it might be a more interesting answer. But anyway, this one is 0. Okay. So that was 46, or no, it was 48, right? 48. Was it 2, 1, or was it 1, 2? In my notes, I have something different. 1, 2, excuse me, not 2, 1. It's 1, 2. Yes. Let's redo it. 1, it's supposed to be 1, 2. So if this is 1, 2, then the vector along here is 3, 3, 3. So this is 3t, 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 3, 3. So the length is 3 root 2. So the stuff's a little bit different. So this is 3t minus 2 to the third, 3 root 2. So, okay, nothing to factor out there. So it's just 12 root 2. Root 2. So 12 root 2, and then there's nothing to factor out there, so it's still just 3t minus 2 to the third dt. All right, so now antiderivative. So over 12, so this is going to be square root 2. Let's double check that. So I think it's 1/12, 3t minus 2 to the fourth. So the derivative here is 4 over 12, 3t minus 2 to the third times 3. Yes. So it's just square root 2. So now at 1, 3 minus 2 is 1 to the fourth, and at 0, minus 2 to the fourth. So this is 1 minus 16. So it's minus 15 root 2. There we go. So this is not the picture. It's up here. That's the C, not this. All right. 48, 49. All right, so this is a vector field line integral. Again, they're doing line segments. For C, I didn't like that all these examples are line segments, but what are you going to do? Well, no, we had the one example that's a helix. Anyway, so 49, find the work done by the vector field x comma 3xy comma minus x minus z on a particle moving along the line segment that goes from 142 to 051. Okay, so here we have vector field f, three-dimensional vector field, x 3xy minus x minus z. And the line segment, the curve that we're working on, goes from 142 out to, now here, when you're talking about this work, this vector line integral, the direction along C matters. Right? If you calculate it in one direction, you get the answer 10. If you calculate it in the other direction, it gives you the negative answer, negative 10. So the direction along the curve matters, but it only just negates it if you did it in the opposite direction. So from 142 to 051. Okay, so we're talking about the line segment in that direction. Okay, so the vector from here to here, right, the vector in that direction is minus 1, 5 minus 4 is 1, 1 minus 2 is minus 1. So the parameterization, so this is C. And here you put a little hat over the C to mean that it's a directed curve. So x is equal to that, xyz is equal to that base point, 142, plus t times this slope vector here. So minus t plus t minus t for 0 less than or equal to t less than or equal to 1. Standard way to parameterize a line segment. Okay, standard way to parameterize that line segment. Okay, the tail point plus t times that slope vector for t going from 0 to 1. The slope vector, which has tail at this point and head at the end point. All right, so the work-related line integral, it's the vector line integral over C, f dot dr. Okay, that's the way to write it independent of the parameterization of C. That's the shorthand notation for it. And there was other notations for this vector line integral, this p dx plus q dy notation, which I don't like so much. But anyway, this is the one I like better, the f dot dr. So this is equal to the integral from a to b, f of, after you've picked the parameterization, r of t, dot r prime of t dt. So not the length of r prime, the dot product of the vector field along r with r prime dt. Right, so this is the vector line integral. It's got the vector field in it. And the way it's calculated is by picking the parameterization and then rewriting it like this. So, well, what's f of r? F of r of t is equal to x, which is 1 minus t, 3xy, which is 3 times x times y, 4 plus t, comma, some space here. So this is r of t. Right, so this here is x, 3x times y, and then minus x minus z. So minus 1 minus t minus 2 minus t. So we can simplify that. So f of r of t is equal to, well, this again is 1 minus t. This is 3 times 4 minus 4 plus 1 minus 3t minus t squared, comma, minus 1 minus 2, and then minus plus t. Oh, no, they don't cancel, sorry. Minus 1 minus 2 is minus 3. And then I have plus t plus 2t. Okay, so that's f of r of t. And then we've got r of t here. And then r prime of t is equal to, well, when it's a line segment, it's just that slope vector. Minus 1, 1, minus 1. Like that. So this is equal to the integral from 0 to 1. F of r of t, which is this thing up here. 1 minus t, 12 minus 9t minus 3t squared, minus 3 plus 2t, dot, minus 1, 1, minus 1, dt. Right, and the dot product of two vectors is, of course, a scalar. Right, so once we evaluate the dot product, then we'll have a scalar integral, which we can calculate. So it's integral from 0 to 1, evaluating the dot product. So t minus 1 plus 12 minus 9t minus 3t squared plus plus times negative 1. Right, so plus 3 minus 2t dt. So integral from 0 to 1, what do we have here? So minus 3t squared minus 2t minus 9t plus t, so minus 10t. All right, minus 11t minus 11t plus t, it's minus 10t. And then I got minus 1 plus 12 plus 3, so plus 15 minus 1, so plus 14 dt. So this is minus t to the third minus 5t squared plus 14t from 0 to 1. So it's minus 1 minus 5 plus 14. So 14 minus 6 is 8. Okay. What number was this? 49. I have something different here. No, what we have in my notes is wrong. This is correct. Right, f is minus x minus z. Minus x minus z is minus 3 plus 2t. I missed the 2t in this other example that I did. So this is t minus 1 plus 12 minus 9t minus 3t squared. It's all wrong. No, that's right. So minus 10t and then minus 1 plus 3 plus 12 is 14. No, that's right. So the whole thing there is 8. So the work done is 8. All right, it's 8:01. Why don't we take a 5-minute break? Come back at 8:06 or 8:07. Okay, we'll meet back here at 8:07. Okay, we are back. Oops. All right. So that was number 49. Oh, let's check the answer in the back. Did it say 8? Yeah, work is 8. So 53, 56. Let's see. 53. The work done by force. Ooh, they've got a three-dimensional vector field. Yeah, three-dimensional vector field. So the work done by force, force field 2y, comma 3x, comma x plus y. So calculate um, 2y, comma 3x, comma, and that was x plus y, in moving an object along what curve C, cosine t, sine t, 1/6. Zero less than or equal to t less than or equal to 2 pi. So this curve is, it's a circle, right? The circle of radius 1 at z equal, on the plane z equal to 1/6. So we've got this curve in the counterclockwise direction looking like that. Okay? Now, as we'll see in the next section, so this is a closed curve. The work done by a vector field moving along a closed curve is always 0. The total work done is always 0. There's some positive work done and some negative work done, but they cancel each other out. That's when the vector field is conservative. This one, is probably not. Let me see. My answer is in my notes here. Yeah, it's not 0. So that's not a conservative vector. Conservative meaning a gradient vector field. This is another name for gradient vector fields called the conservative field. Conservative, I guess, because the line integral is always 0, so work is conserved or something, some sort like that. All right. So the work done along C is the vector line integral f dot dr. And we've got f. F is 2y, 3x, x plus y. But when you calculate it, it's the integral from a to b of f of r of t dot r prime of t dt. So we know f. Now we got to find f of r of t. That's the vector field f along the curve r of t. So it's 2y. So it's 2 sine t. Comma 3x. That's 3 cosine of t. And then x plus y, cosine t plus sine t. And then we've got r of t up there. Is the circle cosine t, sine t, 1/6. R prime of t, therefore, is equal to minus sine of t, cosine of t, 0. Okay, so this is equal to integral from a to b, so that's the domain for t, 0 to 2 pi, 0 to 2 pi, 2 sine t, comma, 3 cosine t, cosine t plus sine t, dot, minus sine t, cosine t, 0, dt. So we evaluate the dot product to, right, the dot product of two vector functions is a scalar function. So it is minus 2 sine squared t plus 3 cosine squared t plus 0 dt. And that is a nasty one. So we can, let us change sine squareds and the sine squareds into cosine squareds. So it's minus 2 times 1 minus cosine squared t plus 3 cosine squared t dt. So this becomes 5 cosine squared t minus 2 dt. So for the antiderivative of cosine squared, we use that double angle formula. So this is 5 halves 1 plus cosine 2t minus 2. So it's integral from 0 to 2 pi. 5 halves cosine 2t, 5 halves minus 2. So 5 halves minus 4 halves is 1/2 t. Okay, what's this integral? Cosine 2t from 0 to 2 pi. Right. Cosine 2t cosine 2t from 0 to 2 pi. Oops, I'm sorry, that's not it. It's 2 full wiggles of the cosine curve, right? So the integral is 0, right? So the integral from 0 to 2 pi of cosine 2t, it's easier when you look at sine, actually, is 0, right? So this is going to be 0, and then a minus a half, plus a half, excuse me, plus a half. So that's just pi. So equals 0 plus 2 pi times a half, which is just pi. Right. check that. Yeah, pi. There's the answer there, 53. The answer is pi. Alrighty. So 53, 56, 69, let's see, 53, 56. Oof. Why did they have a capital T here? Kind of an annoyance. Well, fine. So 56, so that's a scalar line integral. So calculate the scalar line integral 1 over x squared plus y squared plus z squared ds for r of t equal to cosine t sine t, so that standard helix, where did it go? Yeah, cosine t, sine t, t. But it doesn't say how, 0 less than or equal to t less than or equal to this capital T. It doesn't say how far along the helix you're going. Just, you're going as far as whatever t is going to be. Right, so your final answer is going to be in terms of t. Alrighty, so for this one, f of x, y, z is this function here. So f of r of t is 1 over x squared is cosine squared, y squared is sine squared, and then z is equal to t squared. This, of course, being equal to 1. So you get 1 over 1 plus t squared. R of t is what we've got up here. Cosine t, sine t, t. So r prime of t is minus sine t cosine t 1. So now, since it's the scalar line integral, we're interested in the length. So this is sine squared plus cosine squared plus 1. So that's just square root of 2. Okay, so the line integral is equal to the integral from 0 to capital T, f of r of t times the length of r prime of t dt. So it's integral from 0 to capital T, 1 over 1 plus t squared times square root of 2 dt. Antiderivative here, of course, is arctangent of t from 0 to capital T. Well, that's interesting. So it's arctangent of capital T minus arctan of 0, but arctangent of 0 is 0, so it's root 2 arctangent of capital T. So whatever your value of arctangent is supposed to be, that's what the line integral is. And of course, that's a bounded thing. The arctangent is its upper bound is pi over 2. So, yeah, so that's a small, so the value of this is quite small. Right, it's at most square root of 2 times pi over 2. Well, it's actually strictly less than square root of 2 times pi over 2. Alright. So it's 56, 69 is... So, calculate the work done by this vector field F along that path for t between 0 and 1. So 2x, 3y minus z. So what is this curve? So there's 0, 0, 0, and here's 1, 1, 1. So in the xy plane, it's a parabola, and then it's kind of some weird sort of corkscrew wavy path from here to there. And of course, the direction matters in this case. So from 0, 0, 0 to 1, 1, 1. All right, so, well, the work done by the vector field is the vector field line integral f dot dr, which is the integral from a to b f of r of t dot r prime of t dt. Right, so we need to know what these f of r of t things are. So f of r of t is equal to what? So 2x is 2t. 3y is 3t squared. Minus z is minus t to the third. So that's f of r of t. R prime of t is equal to 1, 2t, 3t. 3t squared. Right, so this integral is equal to integral from 0 to 1, 2t, 3t squared minus t to the third dot 1, 2t, 3t squared dt. So that's the integral from 0 to 1, 2t plus 6t to the third minus 3t to the fifth, 135 dt. Antiderivative is t squared plus 6/4 is 3/2 t to the fourth minus 1/2 t to the sixth from 0 to 1. So we've got 1 plus 3/2 minus 1/2, so 2. So 69, answer is 2. 69, answer is 2. Oops. I shouldn't have done that. No, it's fine. All right. 72, I have that 72 is the same, my notes, that 72 is the same problem as 49. Yeah, it is. So same problem as 49. So the next problem is 84. So 84, evaluate the integral over c f dot dr, where f is this and c is any path from, well, this is more a problem for the next section, actually. Why did they put it in here? Well, x squared sine y, x squared sine y, right. But this is really a problem for the next section. Let's hold off on number 4, 84, and look at it in the next section. Why? Because that is a gradient vector field. So they are saying to calculate that line integral where c is any path from -1, 0 to 5, 1. So you might as well make it a line segment from -1, 0 to 5, 1 if they're talking about any path. But then again, if they're talking about any path, the path must not matter. What must matter is where the path begins and where the path ends. So the line integral is path independent, and that only happens in general with gradient vector fields. And this one is indeed a gradient vector field. It's the gradient vector field for x squared sine y minus y to the third. X squared, so the function fxy is x squared sine y minus y to the third. So we'll do that one in the next section. Well, we've only got one more problem in this section. We're on to the next section anyway. So 92. So this is that other notation for the vector field line integral. So number 92. So we're calculating the line integral over c of z squared dx plus y dy plus 2y dz for c given by r of t equal to oh right, yeah, so it's the intersection of the cylinder, so the circle of radius 4 at z equal to 3, and then the line segment from 4043 to minus 40. Huh? From 04, oh no, it's not the whole circle. And then C2 is the line segment. Okay, so 043 to minus 403. But wait a minute, what direction do they want? They're not saying what direction it is. C1 is the intersection of the cylinder of radius 4 and the plane z equal to 3 from 043 to minus 403, but they're not saying in what direction. So for c equal to c1 plus c2, where c1 is hard to draw. 043, so x equal to 0, y equals to 4. So x equal to 0, y is equal to 4. 2, so that's 0, 4, 3, or the other way around. To back over here, I imagine that's the direction they're talking about. Terrible. Let's see if I can draw this. So 0, 4, 3 to minus 4, 0, 3. So that's going in a circle. So they're saying from here to here. They're not. It could be that direction as well. I don't know which one it is. They're not saying. So that's a typo in the book. So we'll just assume it's this way. And then from that point to 0, 1, 5. So this is C1 and that's C2. So they give you this path. That's a quarter of a circle and then a line. Okay, so we need to parameterize this. But what does this mean, first of all? What does this mean here? Okay, this is the vector field line integral. When they write it like this, it's z squared y 2y dot dx dy dz, like that. Right, so that's the way to think of this is, where, so dx dt dy dt dz dt times dt. So this is f dot r prime of t dt, or r dr, r prime of t dt, or dot dr. So this is the line integral of the vector field z squared y 2y dot dr. I don't like this notation so much. I'm not really sure why people use this notation rather than just writing it like that all the time, but there you go. It's maybe a little bit more closely related to Green's theorem or Stokes' theorem, but I don't think it's necessary to use two different notations for this. Well, first thing we have to do is we have to get a parameterization. So let me tell you the parameterization that we'll use here. So the circle starts here, so that's the y-coordinate. So that will be 4 cosine t in the y-coordinate, and then 3 in the z-coordinate. And then in the x-coordinate, we get that. And so this is 0 less than or equal to t less than or equal to pi over 2. So that's a quarter circle starting at 0, 4, 3, and ending at minus 4, 0, 3. Right? So that's the quarter circle right there. So we're picking a parameterization for the circle. There are other parameterizations you can look at. You could also use, this kind of thing. Minus t square root 1 minus t squared, or 4 minus t squared. Yeah. No, this one. Yeah, put it here like that. Yeah, this one's a little different than. Yeah. So this one would also work. T going from 0 to 1. That also gives you. I guess this needs to be 3/4 in that case. This also gives you the circle of radius 4 at z equal to 3. right? Because the x squared plus y squared is going to be equal to 4 in this case. So you could use this parameterization or that parameterization, and either one would work and give you the same exact answer. So that's the first part of the curve. And then the second part of the curve is that line segment. So you start with the tail endpoint, -4, 0, 3, and then you add the t. So plus 4t. And then plus t. And then in the z-coordinate is 3 plus 2t. 0 less than or equal to t less than or equal to 1. Right, so these are the two parameterizations of those two curves. And that's fine, you know, I mean you can split your curve up into two curves, just like how we split integrals up over a certain domain into two subdomains. So you can always do that with any type of integral, just partitioning the domain into two domains for integration. Because addition is commutative, we can always just do that. So the line integral over C of f dot dr is equal to the line integral over the first part, f dot dr, plus the line integral over the second part, f dot dr. So let's try to go through this a little more quickly. Integral from 0 to pi over 2. So f is z squared y 2y. So for R1, it's z squared, which is 9. Y is 4 cosine t. 2y is 8 cosine t. Dot R prime is minus 4 cosine t minus 4 sine t 0 dt. Plus the integral over the second part, z squared is 3 plus 2t, y and 2y, t and 2t, dot r prime, which in this case is 4, 1, 2, right? 4, 1, 2, dt. So we've got these two integrals here, and we're going to add. So this is equal to the integral from 0 to pi over 2. So minus 36 cosine t minus 16 sine t cosine t and then 0. Integral from 0 to 1. 4 times 3, 2t plus 3 squared, plus t plus 4t, you get 5t dt. Oh, I think I'm supposed to square something. Oh, the 9 is the square there. Minus 36 cosine t minus 16 sine t cosine t. All right, so antiderivative here, antiderivative minus cosine is minus sine. Sine t cosine t derivative is 1/2 sine squared t. All right, the derivative of that is 2 sine t cosine t from 0 to pi over 2. And, well, this one I have to write out the whole thing, right? So that's 4t squared, so 16t squared 6 times 2 is 12 times 4 plus 48t. 48 plus 5 is 53t. Plus 9 times 4 is 36. So at pi over 2, you have minus 36 and minus 8. Those are both 1. And then at 0, they're both 0. Plus, antiderivative here, 16 thirds t to the third plus 53 halves t squared plus 36t from 0 to 1. So this is minus 44 plus 16 thirds plus 53 halves plus 36. So that's equal to, some equal to something. Okay, so that's all we have time for today. I know the calculation on that one was a little bit hairy, and I rushed through it. But one takeaway from this that I want you to remember is that, like, if a curve is presented in two parts like that, the first part is a circle, second part is a line. They're just two different things. First part is a parabola, the other part is a circle, whatever it might be. You can always calculate the line integral over the whole curve as the sum of the line integrals over the first part plus the second part, right? Because addition is commutative and an integral is just a Riemann sum along the whole domain. So you might as well take the Riemann sum along this part of the domain plus the Riemann sum along that part of the domain. So the entire integral is the sum of the two integrals over the different domains. With any type of integration problem, it always goes like that, if you need it to. Okay. All right. So please, guys, spend some extra time on this. If you spent X hours studying chapter 5, you're going to need like 3X hours studying this. Okay. Chapter 6 is conceptually, it's got a lot going on. It's not like harder than the rest of the course. It's just conceptually different. So you just need the time to wrap your head around it. So if you spent N hours studying before, you need to spend like 3N hours now. Okay? Please keep up. Please, do these problems. I'll have some time for review hopefully at the end, and I'll have a study guide for you for the 4th exam as well. Okay? And I'll send more information over the email. Have a good night, and I will see you on Wednesday.